you are listening to the beat of my heart. If you timed your heart, you'd find that it beats about once every second. But the motion of the heart is not completely regular. It is not exactly the same from one beat to the next. Here's a graph of a heart beating, an electrocardiogram. You can see from this that the heart's motion is complicated, but it does repeat itself, but not exactly. The time, for instance, for these two beats is not identical. In this film, we're going to talk about motions which do repeat themselves exactly, motions which are periodic. Here's a graph of a periodic motion. Periodic motions, no matter how complicated, can be analyzed in terms of a particular kind of periodic motion, which is called simple harmonic motion. More than simple harmonic motion itself occurs frequently in nature, so an understanding of this type of motion is important. I'm going to show you a few examples of periodic motion. This ball is suspended by a very long spring. Its period of vibration is about 4 seconds, so that its frequency of vibration is about 1/4 of a cycle per second. Over here, there's an inertial balance. It vibrates with a period of about 1 second. This tuning fork vibrates much more quickly. I can't tell by eye here what the period is, but it says on the fork that it makes 440 vibrations per second, and therefore its period must be 1/440th of a second. The period of this bouncing ball is about 1/2 a second. But as you can see, the period keeps on decreasing, and therefore this isn't a good example of periodic motion. Over here, there is a periodic motion which you have already studied. The motion of this ball repeats itself exactly with a period of 5 seconds. This is uniform circular motion. You know how to describe this motion completely. You can actually write down equations which describe this motion. But what about the other periodic motions that I have shown you? Can you write down equations which describe them? This spot is moving with the particular kind of motion that is called simple harmonic motion. How can I describe this motion? Well, to describe any motion completely, I just have to know how the displacement changes with time. And this apparatus is arranged so that the pen attached to the moving spot will plot a displacement time graph. This glass plate is movable, and I'm going to set it moving in this direction with a constant velocity. The distance that it travels in this direction will be proportional to the time of travel. The pen will be moving up and down in simple harmonic motion, but in each instant of time, the glass plate will move along in this direction a fixed distance. The trace that the pen makes will be a displacement time graph of simple harmonic motion. Now I'm going to set the plate moving. Very nice. You sure this is simple harmonic motion? Oh, I guarantee it. I have it on good authority that this is a displacement time graph for simple harmonic motion. Now I'm going to use this graph to find out how to write an equation which describes simple harmonic motion. I drew axes on here earlier, a vertical axis and a horizontal axis. The pen first touched the plate up here,
So time is plotted in this direction. Displacement is plotted in this direction. Displacement x. And I've chosen the zero of displacement so that the maximum displacement this way is the same as the maximum displacement this way. I'll call the upward direction positive, the downward direction negative. Now you know how to find velocity from a displacement time graph. The slope of this graph at any point gives the velocity at that point. So down here, I'm going to plot a velocity time graph. I've put in these vertical lines to help me. They are spaced 1/4 period apart. Remember, this much is one period, then the motion starts over again. To start with, the tangent is horizontal. The slope is 0, so the velocity is 0. This, of course, is where the spot in simple harmonic motion stopped and started in the other direction. Then, a 1/4 period later, here, the tangent is steepest, and the slope is negative. I haven't specified what the scale of velocity is here, but I will suppose that the magnitude of the slope, that is the velocity, is this much. Then another 1/4 period, the slope, the velocity, is 0 again. Another 1/4 period, and the slope is now positive. I think you can see from the symmetry of this graph that the magnitude of the slope here is the same as the magnitude of the slope here. But here, the velocity is positive. Then another 1/4 period, the slope is 0 again, and I have come one full period. Then the motion repeats itself. Of course, I can't join these points with straight lines because the velocity is changing continuously here. I could plot more points in between. And if I did make these measurements, I'd find a curve that looked something like this. This is the velocity time graph for simple harmonic motion. I think you can see that it has the same shape as the displacement time graph, but the velocity graph is displaced this way 1/4 period. When the displacement is a maximum, the velocity is 0. When the displacement is 0, the velocity is a maximum downward or upward. The spot in simple harmonic motion is moving fastest at the center of the motion. Now, what can I find out from this graph? The slope of a velocity time graph at any point gives the acceleration at that point. So down here, I'm going to plot an acceleration time graph. I could do this, as I did before, by taking slopes here, but this time I don't have to. This graph is the same shape as this graph, so that when I take slopes from this graph, I'll just get another graph of the same shape, but displaced another 1/4 period. It will look something like this. It's difficult to do a good job of these graphs without actually measuring the slope at a large number of points. These, of course, are just rough sketches. But I did do this carefully before. These are the graphs that I obtained. The scale that I've used to plot acceleration is arbitrary. It's arbitrary for each of these graphs. But I have chosen the acceleration scale so that the size of the acceleration graph is exactly the same as the size of the displacement graph. And now I can show you what I mean when I say that these graphs have the same shape but are shifted. They do have the same shape. The fact that these graphs have the same shape but shifted 1/4 period is characteristic of just one kind of periodic motion. Any periodic motion that behaves in this way is simple harmonic motion. Each of these graphs describes simple harmonic motion, but I want a mathematical relation to describe simple harmonic motion. How can I find this? I want you to compare the acceleration graph and the displacement graph. When the displacement is a maximum, the acceleration is a maximum too, but in the opposite direction. As the displacement decreases, the acceleration in magnitude decreases. They both become zero together. The magnitude of the acceleration is always proportional to displacement, but the acceleration is always in the opposite direction to displacement. How can I express this mathematically? Like this. Acceleration is proportional to the negative of displacement. This mathematical relation defines simple harmonic motion. Now what about force? All of this has just been the kinematics of simple harmonic motion. What about the dynamics of simple harmonic motion? Whenever a mass is moving with this kind of motion, what sort of force must be acting on the mass? Well, whenever an unbalanced force acts on a mass, according to Newton's law, the force is proportional to the acceleration. Now I want you to compare these two expressions. I think you can see that whenever a mass is in simple harmonic motion, there must be an unbalanced force on it which is proportional to the negative of displacement. F is proportional to minus x. Now I'm going to write this expression as an equation. I can do this by introducing a proportionality constant, K. This is called the force constant for the particular simple harmonic motion. Whenever a force behaves in this way, there must be simple harmonic motion. Now, Dr. Hume has an experiment set up so that we can measure some forces.
This is periodic motion. Is it simple harmonic motion?
This is the equilibrium position of this puck. If it's displaced away from me, the springs exert a force on it towards me. If the puck is displaced towards me, the springs exert a force on it away from me. The springs exert a restoring force on the puck, and a restoring force is necessary for simple harmonic motion. But as I showed you, for simple harmonic motion, the restoring force must be proportional to the displacement. And to see whether it is here, we'll have to make some measurements. This scale will show the displacement of the puck in centimeters.
This is a spring balance, and it's calibrated in newtons. I'm going to hook it onto the puck and pull the puck away from its equilibrium position and measure the force. It's now at the 10 centimeter mark, and the force is 1.1 newton.
1.1.
20 centimeters, 2.2 newtons.
2.2.
30 centimeters, 3.4 newtons.
3.4.
40 centimeters, 4.6 newtons.
4.6. You can see that here the restoring force is proportional to the displacement. This means that this motion must be simple harmonic motion. If we plotted a displacement time graph for this motion, it would look exactly like the displacement time graph that we plotted before. Now, what about the period of this motion? What would you expect the period to depend on? Dr. Hume has been putting a lead ring on the puck. Would you expect the period of this motion to be larger or smaller than before? I think you can guess that with a larger mass, more inertia, the motion is more sluggish. The period is larger than it was before. It's still simple harmonic motion, but of a different period. Suppose that I used a stiffer spring here. What would that do to the period? Well, when the puck is displaced, the restoring force on it would be larger, the motion would be quicker, the period would be less. But just how does the period depend on these quantities? We'll have another look at the equations. So far, I don't have an equation for acceleration, but I can derive one. Force is equal to this, but always, as I said before, by Newton's law, unbalanced force is equal to mass times acceleration. And I want you to compare these two expressions for force. Equating these, acceleration is equal to minus k over m times displacement. This equation, just like this expression, defines simple harmonic motion. But in neither one of these expressions can you see the period, the thing that's easiest to measure. It turns out that it is possible, by mathematical means, to derive an expression for the period from this equation. But the mathematics is mathematics you probably haven't studied yet, so we're going to have to get at the period another way. We are going to do it by using what you already know about another kind of motion, uniform circular motion.
You can see that there's a connection between uniform circular motion and simple harmonic motion. Now I'm going to ask you to use your knowledge of this motion to analyze simple harmonic motion. Usually, we work the other way around and find out about motion in a curved path by analyzing it into its component motions in straight lines. I'll show you what I mean. Here's a model of a ball shot horizontally. The model shows the position of the ball at equal intervals of time. You know that you can calculate this motion by thinking of two independent motions. One in this direction, the horizontal component, and one in this direction, the vertical component. Now look at the model from another direction. It looks like a ball falling straight down with constant acceleration, the acceleration due to gravity. You are seeing the vertical component of the motion. Now I'll turn the model so that you can look down from above. It looks like a ball moving with constant velocity. You are seeing the horizontal component of the motion. This curved motion can be analyzed into these two independent components. You can think of circular motion as having a horizontal component and a vertical component. When I turn this sideways, you see the vertical component of the motion. the spot appears to move up and down in a line, and it looks like simple harmonic motion. Let's investigate. I'm going to put some vectors on this circle one at a time, and they will represent the displacement, the velocity, and the acceleration of the spot moving in uniform circular motion. And when you look sideways at these vectors, they will represent the displacement, the velocity, and the acceleration of the vertical component of circular motion. First, the displacement. The magnitude of the displacement vector is equal to r, the radius of the circle, and it points from the center out to the moving spot. Now watch the vertical component of the displacement vector. Now it's 0. Now it's positive. Now it's 0. Now it's negative. You are seeing the displacement vector that Dr. Ivy has called x. It points from the 0 position out to the moving spot. Now the velocity. This stick will represent the velocity vector. Remember that the velocity is always tangent to the circle, and that it remains constant in magnitude as the spot moves around. Now watch the vertical component of the velocity vector. Now it's 0. Now it's a maximum. Now it's 0 again. It's a maximum at the center of the motion and 0 at the ends. This is the way the velocity varies in simple harmonic motion. What about acceleration? I'll take off the velocity vector now. This will represent the acceleration. The acceleration of the spot moving in the circle is constant in magnitude. And it points towards the center of the circle. Now watch the vertical component of the acceleration. Now it's 0. Now it's a maximum. Now it's 0. Now it's a maximum. When the displacement is 0, the acceleration is 0. When the displacement is a maximum, the acceleration is a maximum. When the displacement is downward, the acceleration is upward. And when the displacement is upward, the acceleration is downward. Now, to help you to see that the acceleration is proportional to the displacement, I'm going to repeat this. I can make this acceleration vector to any scale that I want. So I'm going to use one which is exactly equal in length to the displacement vector. Now you see it as equal to the displacement x, but pointing in the opposite direction. The acceleration is exactly proportional to the displacement, but in the opposite direction. This vertical component of uniform circular motion fits exactly the definition of simple harmonic motion. A is proportional to minus x. In fact, we use circular motion to produce the simple harmonic motion that you saw before. The pen moves up and down in such a way that it always has the vertical component of the motion of the spot which moves uniformly in the circle. The reason for looking at circular motion was to find an expression for the period of simple harmonic motion. The period of this simple harmonic motion is the same as the period of this circular motion. The length of this acceleration vector is equal to r, the radius of the circle. I chose the scale to make it this way. But you know that in fact this acceleration is equal to 4 pi squared over t squared times r. This is the scale factor, and t is the period. And the whole thing is the centripetal acceleration. Now, with this same scaling, you saw the vertical component of acceleration as equal in length to the displacement x. Now, the same scale factor must apply. This is the magnitude of the acceleration in simple harmonic motion. The acceleration is in the opposite direction to the displacement, so the vector A is equal to minus 4 pi squared over t squared times the vector x. Now I'm going to compare this expression for acceleration with the one that Dr. Ivy had. These are both expressions relating acceleration and displacement in simple harmonic motion, so they must be equivalent. My expression is based on kinematics. I derived it using your knowledge of circular motion. So mass and force are not involved. Dr. Ivy introduced Newton's law, dynamics. So in his expression, mass and force constant appear. Now I'm going to compare these two expressions, and you can see that k over m must be equal to 4 pi squared over t squared. This means that t squared is equal to 4 pi squared m over k. Now I have to take the square root. T is equal to 2 pi into the root of m over k. Finally, we have it, an expression for the period t. The period of a mass m moving in simple harmonic motion under the influence of a restoring force whose force constant is k.
Now you know how the period depends on mass and force constant. As I suggested before, by intuition, for a larger mass, the period is larger, the motion is more sluggish. For a stiffer spring, the period is less, the motion is quicker. I've been doing some calculations for this particular simple harmonic motion of this puck. First of all, from the data that we had before, I calculated the force constant, K. A force of 4.6 newtons gave a deflection of 40 centimeters, or 0.4 meters, so that the spring constant, or force constant, is 11.5 newtons per meter. Then I used that in here for force constant. I weighed the puck. Its mass was 3.67 kilograms. Then I did the arithmetic, and the period came out to be 3.54 seconds. Now I'm going to measure the period and see if this is what I get. Zero. 1. 2. 3. 4. 13 seconds. So the period is 3.6 seconds, which, as closely as experimental error will allow, is equal to 3.54 seconds. So we get the same value calculated as experimentally as we must do. We have done the theory of simple harmonic motion.
Here is a periodic motion that's very familiar. I am a pendulum. Is this simple harmonic motion? Remember, whenever simple harmonic motion occurs, there must be a restoring force proportional to the displacement. Here, there is a restoring force, all right. And this arises because of gravity. But is the restoring force proportional to the displacement? Well, for small vibrations of a pendulum, it is. So the motion of a pendulum with small vibrations is simple harmonic motion. The larger the vibrations, the less true this is. The period in simple harmonic motion depends on the mass vibrating and the force constant of the system. Watch what happens here when we double the mass.
Double the mass?
Yeah, well, more or less.
If you timed us now, you would find that the period is exactly the same as it was before I got on. The period here is independent of the mass. And this is because I have changed the force constant, too. The force constant here depends on the force of gravity on us. That is, on our weight. And when I increase the mass, I also increase the weight in proportion. The period of a pendulum does not depend on the mass vibrating, but it does depend on the length of the pendulum.